Hi, welcome to the second part of the relationships lecture. We're going to start now by using lines to summarize the relationship that we've been seeing in a scatter plot. Sometimes we can make some very interesting projections and summarizations by using a line equation instead of just eyeballing a scatter plot. The name of the line, or the best summary line that we have through the cloud of points, is called the least squares line. And it's called this because we're going to be using a version of the line that minimizes the sum of the squared distances from the points to the line. Remember that the equation of a line is y equals an intercept a plus a slope b times x. This is a little bit different than the usual mx plus b that you might have seen in a math class in high school. Here's an overview of the things that we are going to be studying in this section. We're going to be studying and learning how to interpret the estimated slope, the estimated intercept, how to use the equation of the line to make a prediction about y, the response, understand residuals, r squared, a measure of size for a typical residual, and then we'll study some outliers and influential points. Here's some data that we usually show in class with a little video about a girl named Sarah who had growth hormone deficiency, and the doctors treated her for the growth hormone deficiency, and we studied her growth pattern over time. Her age here is in months, and the vertical axis, the response variable, is her height in centimeters. And here are some points measured on her over time. You can see the points follow a pretty clear straight line pattern, which might suggest that using a straight line to summarize her growth, at least at this point in her life, is a reasonable thing to do. And so this line that runs through the points might be a really good way to summarize her growth relationship. So we load those data into R with a data frame called STAT, and then we will estimate a summary line using age as the predictor to summarize a response variable, height. So the y variable is height, explained, the tilde or the wiggle is the explained by as a function of age, and we make a summary object summarizing this line and how well it goes to the points in an R quantity called Sarah mod, and then we summarize it. Right here we do summary of Sarah mod, and we look at the coefficients of the line, and what we see from this output is an estimated intercept of 71.95 centimeters. That's the y-intercept. When this line goes back to 0 months of age, that's the value where the line cuts the y height axis, and the slope of this line is is in the row called age, and it's 0.3833. It means that for every additional month of age, Sarah grows by 0.3833 centimeters. And so this slide, number 42, talks about that interpretation that I just gave you about the slope. The slope, of course, of any line is the change in y over a change in x, and in particular maybe a unit, 1 unit increase in x. And this slope number b is measured in the units of y. So because in this case the units of y for Sarah's height are in centimeters, the slope of the line 0.3833 is in the units of centimeters. And the way you will interpret it and the way you'll write about it for me on exams and homeworks is that as Sarah's age, the x variable, increases by 1 unit, and a unit here is month. Please don't write in your writing and say a unit. Give what the unit is. In this case, it's a month of age. Her estimated height is going to increase by 0.3833, the value of slope. If the slope would be a negative number, it would mean that there is a decrease in the response. On this overhead, I'm going to interpret the intercept for you, but I'll just warn you in advance that the intercept very rarely makes sense. In the third bullet, I'm warning you it doesn't always make sense. In practice, I've very rarely ever had the intercept really make sense, and it's usually not a very important or relevant thing to interpret. I just want you to be able to do it if it does make sense for your particular context. Again, a y-intercept is what do we project the y response value to be when the predictor is 0. In the Sarah data example, the predictor variable age being 0 means essentially at birth, and we would estimate Sarah's height at birth to be 71.95 centimeters, and that's the interpretation. That's a really silly interpretation, and it just doesn't make sense. 72 centimeters is an absolutely enormous newborn baby, and that just doesn't fit, and we'll talk about why that is really foolish a little bit later in this presentation. One of the other things that we'll want to do with the line, probably one of the most important things, is predict what the response value is going to be for a particular value of x. And so what you do is you use the equation of the line and you plug in the value of x that you're interested in. Here in the third bullet, you can see we've got an equation that summarizes the y variable to be an intercept of 2 plus a slope of 3 times the value of the predictor. Well, if that's the summary equation of the relationship, the straight line that summarizes the relationship, if we plug in a value of x equals 5, right in here for the value of x, we'll have 3 times 5, which is 15, and then we add 2 to it, and that will give us an estimated response of 17. Whenever we estimate something in statistics, we put a hat on it. And so our estimated value of y for a observation that would have an x value of 5 would be 17. Using the Sarah least squares line, what do we think her height would be at 36 months? Well, if we go back to the scatter plot, I can kind of show you what we're doing. 36 months is back here. What do we estimate her height to be? Well, it looks like it's going to be about 86 centimeters. And if we plug in 36 for months for x, the slope is 0.3833. We multiply those two numbers together. We add 71.95 for the intercept, and we get an estimated height of just about 86 centimeters, 85.75 centimeters. You can use R, the computer program, to make this prediction. All you need to do is use the predict command, the estimated model object that we created using the data and putting a line through those data, and then we give a new observation for age. Age equals a list of values with one thing in the list. The little c means a list, combine or concatenate a list of numbers together, and there's only one in this list, 36 months, and so we get an estimated height of 85.75 centimeters. What do we estimate Sarah's height to be when she's a really old lady at 90 years of age? 90 years times 12 months in a year is about 1,080 months. If we use the line to project her age 90 height, we would plug in 1,080 months in for x, multiply by the slope, add an intercept to it, and we get about 486 centimeters. That's about 5 meters of height. And just so you know, I'm a full-grown, very tall guy, about 6 feet 6 inches, and I'm almost 2 meters in height. This is saying that when she's an old lady, we estimate Sarah to be about the same height as a small building. And this clearly makes no sense. And the reason it makes no sense is we're projecting Sarah's growth continues through adulthood, and just like it did in childhood. And that is something that's just not justified. As we all know, people stop growing, their vertical height stops after a certain point, and the relationship flattens out, and it doesn't continue in a linear fashion. This kind of projecting a relationship is happening beyond where we have any data for Sarah. Remember, for Sarah, we have observations for her that run from about 35 months up to about 60 months of age. 1,000 months of age is way beyond the scale of where we have any evidence about this relationship. And when we make statements or project beyond where we have any kind of predictor variable data, that's called an extrapolation. And we get really foolish results sometimes when we do that, when the relationship doesn't hold. Here's sort of an illustration of what I'm talking about. If we have a relationship for height of boys when they're children and adolescents, and we project that out to when they're adults, we would have an enormous height projection, but of course what happens is growth slows down, and projecting beyond where we have any data will create a very silly estimation. So when a prediction is made outside the range of where we have predictor variable evidence, it's called an extrapolation. The same thing was happening back when we were trying to interpret Sarah's intercept. Remember I said that's an enormous newborn baby? Well, the reason it's a terrible projection is because the relationship is not the same when she's a newborn baby. It just doesn't make any sense to think Sarah's mother giving birth to something like the size of a 4th grade child. The relationship during the part of childhood where we have data on Sarah is not the same as it is back when they're a newborn. If you look back at the growth curve that I showed you, you can see that when babies are newborn, the growth relationship is much steeper and it's not exactly linear. And so projecting what will happen back at birth is a dangerous activity that is an extrapolation, and that's why we get such foolish values for the intercept and also such foolish values for when she's an old lady. Another nice thing about using a least squares line summary is that if we have a mathematical structure to describe the relationship, we can speculate on blood alcohol content for beer consumptions that aren't even in our data set. Remember, the beer alcohol consumption problem had whole numbers of beers consumed, and we had blood alcohol content for the number of beers consumed. What if we wanted to project the blood alcohol content at a value like 6.5 beers, where we really don't have any students or anybody drinking that much? We could use the mathematical structure of the line to predict what the blood alcohol content would be out here at about 6.5 beers. We could use the line to project that, even though we really don't have any data exactly at 6.5 beers. If we use the least squares line to project this, we get about a 0.10 alcohol level, and you can see that's pretty reasonable projection for 6.5 beers. Here's how you would do it. You'd estimate a summary line using the LM function, blood alcohol content being as the response explained by the beers variable, and once we have the blood alcohol content model object, we use the predict function on that summary object for a beer value of 6.5, and we get a 0.104 estimate. This is plugging in the least squares line for x equals 6.5. Another important concept in studying line relationships is the concept of a residual. The definition is given here. It is for the ith data point, the ith data case. It's simply the difference between the actual value of the response variable, y subscript I, and the estimated value of y from our least squares line. So it's observed minus expected response value. And residuals are just basically these little vertical distances between the data points and the summary line. The one I'm talking about right here, the red dot, is the actual value of y for this observation. Looks like it's about 81.1 units, centimeters. It looks like we would estimate this height to be about 80.8 centimeters. And the difference between what actually happened on the red dot and what we would have expected from the summary line when the age was 25 months, that distance or difference is the residual. When points are above the line, the residuals are positive numbers. In a case like this one here, the data point at 24 months of age, the actual height was less than what we were expecting, and the residual is a negative number. If a point is right on the summary line and what actually happens is what we expect, the residual is 0. And so here's the summary of that. Residuals can be positive, negative, or 0, depending on whether the actual data value is above or below or right on the least squares line. When we look at an example from Sarah, we will notice that Sarah was 86 centimeters of height at 36 months. That's this data point right down here. And notice that that data point, her height, is just a little bit above the summary line. And remember, we projected the summary estimated height to be 85.75 centimeters. That means the residual for this observation right down here in the lower corner is the actual height of 86 centimeters minus what we would project from the least squares summary line, plugging in 36 months, 85.75 centimeters, for a residual of positive 0.25 centimeters. And notice that's just a very small amount higher than what we were expecting. How do we get all this stuff? Well, we have the estimated summary model for Sarah. We have the prediction, the y hat, for when she's 36 months of age. And so the residual would just be the actual of 86 minus the predicted, for a residual of 0.25. What we're doing when we make the summary line is we're trying to put a line through the points so that the residuals are as small as we can get. Actually, the sum of the squared residuals is as small as we can get. And that's how the line is decided where it should go through the points, and therefore what the intercept and the slope should be for it. These are some sort of complicated equations and formulas for what the right slope and intercept will be for the least squares lines. The best slope, this should be a little b here, is a complicated formula of variation, joint variation between y and x, divided by a very complicated formula of variation for the predictor values. And this is the estimated intercept. When you ask R to make a linear summary model like we do in the LM command, for example right here back in overhead 55, the R software is doing this kind of computation behind the scenes. Another important quantity that we use in our work is the size of a typical residual. It's often very important to make decisions about whether observations in the scatter plot are unusual or strange. And in order to make that decision, you sort of need to know how much variation is happening on these residuals. How big are the residuals and how much variation do they have? And so this is a quantity that is a measure of how big a typical residual would be. If you look inside the square root formula, you are adding up a bunch of squared residuals, and you're dividing by almost the number of items that you're adding up, so that inside here is almost like an average squared residual. And when you take the square root, it's like an average residual. And so this quantity is measuring how far above and below a least squares line are y values in this data set. How far are points above or below the least squares line? And that is a very useful summary distance measure to have. Notice that the smallest that this measure could ever be is 0. If every y value was exactly what we were expecting, you would have residuals of 0, and the size of a typical residual, of course, would be 0. Smaller values of this S would mean that the line is a better summary of the data. So the way we interpret this is the size of a typical residual, and it's the typical distance of a y value above or below the least squares line. From the blood alcohol data, the size of a typical residual is 0.0204, and that means that blood alcohol contents are typically about 0.02 units above or below the least squares summary. And if we look at the blood alcohol data right here on overhead 50, you will see that the size of a typical residual is probably something like about this distance between this point and the line. And if you think about how big this vertical distance is on this scale, that's about 0.02 units. If we take a look at the same thing for Sarah, the size of a typical residual is about 0.387 centimeters. And if you look at Sarah's scatter plot, you will notice that a typical residual is about, say, like this point away from the line. And that is a very small amount. That's certainly less than 1 centimeter. And that's what we're observing here from this summary amount. That's how far the points are from the line. That's a very important concept that you'll need to know how to explain. Another important value is r squared, and r squared measures the strength of the relationship between the response and the predictor. Now you might ask yourself, well, haven't we done this before with the correlation coefficient? And you have, and if you notice this formula, capital R squared, the thing we're talking about right now, is really the correlation coefficient, little r, squared. So it's a function of the correlation coefficient. The reason we use it is it has a little bit better interpretation. We can interpret this number to be the proportion or the percentage of variation in the response that can be explained by the values of the predictor. And this formula just basically says that what's going on is it involves the fraction of unexplained variation compared to the total variation, and we get a fraction or a percentage out of it. And so this next to last bullet right here is a very important interpretation of this value. It basically tells you how well the predictor variable explains the response. When we look for this in output in R, it's called multiple R squared. Please don't be confused by the adjusted R squared that is also in the output. We don't use that one. We use multiple R squared. From our example so far, R squared from the blood alcohol problem was 0.7998, and the interpretation is that the number of beers consumed explains 79.98% of the variation in blood alcohol content. You could phrase it the other way around and say that this one's probably better. 79.98% of the variation in the response blood alcohol content is explained by the number of beers consumed. It is really important to make sure that you say that this is the percentage of variation in the response that's explained by the predictor. For Sarah's growth, it means that 98.88% of the variation in Sarah's heights can be explained by her age. And that is almost a value of 1, or 100%. I should have mentioned back on this overhead that r squared can take on a value between 0 and 1, and if you change that to a percentage, that's between 0 and 100%. So for Sarah's data, knowing the age is almost a perfect projection of what her height will be. Knowing her age almost perfectly predicts Sarah's height. R squared is very big. Here's where you'll find it on output. Here is Sarah's estimated summary model using age to explain height, and when you summarize that line object, Sarah mod, you'll see multiple r squared right down here of 0.989. Right above it, you'll see residual standard error. That's the value of S, or the typical residual that we've been talking about. So on this overhead, overhead 62, the numbers you really need to know about and be able to summarize are the estimated intercept A right here, the estimated slope B right here, the size of a typical residual S, and r squared. These four numbers are the big numbers you need to understand from this output. From the blood alcohol example, the size of a typical residual is right here, 0.02, and the r squared is roughly about 0.8, or 80% of the variation in blood alcohol content can be explained by the number of beers consumed. Another example that I've prepared for you is some data about manatee deaths in Florida, and I'm going to read in a CSV file, which is like an Excel file. CSV stands for comma separated values, and the Excel spreadsheet program understands how to organize data like that, and you can view a data set within Excel if it's in CSV format. And I'm going to read that data into R. When it says header equals true, that's nothing about soccer. That just means the names of the variables are on top of each column of the spreadsheet. And here's a little preview about what's in the manatee data frame. We have some years, we have a variable called boats, and we have a variable keeping track of the number of manatees killed in the state of Florida. The year range is from 1977 to 1994, and we're going to study the relationship between powerboat registrations. The boats variable is the predictor. How many powerboats were registered in the state of Florida? These numbers that are down here are in thousands. So 500 means 500,000 powerboat registrations in Florida, 500,000 powerboats. The vertical axis is the number of manatees killed. And what you can see from this display is there's a very clear positive linear upward pattern. More powerboats in Florida translate to more manatees killed. And here is the summary line. Let's talk about some of the things about the line from this estimating a summary line using boats to explain killed, and then we have a summary of our manatee model. We have the estimated intercept of -35. We have a slope of 0.1127 connecting the tilt and the slope of the line. Size of a typical residual is about 5.4 manatees killed, and multiple r squared is about 0.833. If you wanted to compute correlation, like I have at the bottom here, with the manatee data frame, the correlation between the number of manatees killed and the number of powerboats is about 0.913, very strong correlation. So let's interpret all the stuff we've been learning about. The slope is about 0.113, and that means if you increase the predictor variable, powerboat registrations, by 1 unit, remember a unit is 1,000 registrations. So 1,000 more powerboats registered translates to an additional 0.113 deaths. That's a really hard number to sort of think about. How many deaths is that? That's not very many powerboats registered. You might do better understanding what's going on if you think about not just 1,000 more powerboats, but what about 10,000 more powerboats registered? That translates to moving this decimal place on the rate of change in y over change in x. If x changes by 10 units, that means that y, the manatees killed, changes by 10 times this, or 1.13 manatee deaths. So about an additional death for every 10,000 boats. If you have 100,000 more boats, you get about 11.3 additional manatee deaths. And that looks pretty reasonable if we think about it. 100,000 more boats is like going from 500 to 600,000 registrations, and that's like going from about 20 deaths to about 31 deaths, and that's about 11 additional deaths. The estimated intercept, as usual, doesn't have a very reasonable interpretation. It just doesn't really seem to make very much sense that if there were 0 powerboats registered in Florida, that's what X0 would mean, the estimated number of manatees killed would be a negative 35 deaths. I'm not sure how we can have negative 35 deaths. Some students like to try to argue to me that that means there's a growth of 35, but I think it just is another problem trying to interpret the intercept when we're doing a really bad extrapolation back at 0 powerboats. R squared for our problem is 0.833. The interpretation that you need to be able to give is like the bullet number 4 here. 83.3% of the variation in manatee deaths can be explained by knowing the powerboat registrations in Florida. You really need to have the variation in the response being explained is crucial. I will mark off if this part of the phrase is not there. So please copy and understand this way of communicating R squared. The size of a typical residual is about 5.4 deaths in this data set. Remember, I got that from right here, 5.4. Here's the R squared. Going back to R squared for a minute, this is a pretty big percentage. 83.3% is a pretty big percentage of variation. So manatee death values are largely explained, the variation is largely explained by the number of powerboats. It's a very strong predictor. Other things are involved. This is not 100% of the variation explained by boating, but the number of powerboats is really strongly connected to the manatee deaths. Now, the size of a typical residual is about 5.4 deaths, and if you look at the graph, that is saying that the typical size of points around this line is about 5 deaths. And 5 deaths is about between 25 and 20. That's about 5 deaths. And that's about how much these points are drifting above and below the least squares line. So let's do some work. If Florida decides to restrict the number of powerboat registrations to 716,000 boats, how many manatees do you think will die? Well, that means we need to plug 716. Remember, that's in hundreds, or that's in thousands. And so plugging 716 in for x, multiplying by the slope, adding the intercept, gives us about 45.5 deaths. If you had a year where there were 34 actual deaths, what's the residual? Well, the residual will be the actual number of deaths of 34 minus the predicted of 45.508, and that would be a residual of about negative 11.508 deaths. And that means that the actual number of deaths was about 11.5 under the line, less than what the line suggested. Is this, is this unusual? This was under the situation of special protection measures and speed limits and protection for manatees. Did this intervention seem to help? Well, the question is a value like this below the line, is that very much below the line? Because if you're having notably fewer manatee deaths in a year where there were special rules, maybe the rules are helping stop manatee deaths. If a data point is sort of close and just a little bit under the line, like this one, I don't think we should really jump to a conclusion that the special regulations were very helpful. So how are we going to be able to tell if 11.5 deaths are very much below the line or just a little bit? The key is, how big is typical variation? Typical variation is about 5.5 deaths. So 11 deaths below the line is about 2 standard deviations, or 2 sigmas, 2 standard deviations below the least squares line. And that is a pretty big z-score size of variation below what's expected, and we would conclude that that is probably suggesting evidence of prevention of deaths. It's enough below the line to be noteworthy. Usually we say things that are more than 2 standard deviations to be unusual and substantial, like we learned in the first section. In this discussion now, in this example, we're going to be talking about individual cases. The horizontal axis variable is for some children. How long did it take them to say their first words in months? And so this is age at first word. Remember, 12 months would be 1 year of age. And the vertical axis is an intelligence cognitive skill measure, typically used in psychology. And you can see from this display that children that take a long time to say things and speak tend to have lower intelligence levels. And there are some data cases, 19, 2, and 18, that are specially marked here. And we're going to talk about these special cases. So what's going on with child number 18 way down here in this corner? Well, what does it mean to be down here in the corner? Well, it means that it took over 40 months to speak for this child. They took a long time to talk. The first words were something like, "Dad, can I borrow the car?" It took a long time for this child to speak, and when the child did speak, the intelligence measure for that child is really quite low. So this is a very unusual case. Case 19 is also very unusual. This child spoke at about 16 months, and that is not too unusual. There's lots of other children taking till about 16, 18 months to speak. But the intelligence of child 19 is abnormally high. The Giselle adaptive score is much higher than what we would have expected. We would have expected something about 90 from this child, and we got something about 120. So very unusual case. Child 18 took much longer to speak than anyone else and has a much lower intelligence level than anyone else. And this is an unusual case also. We're going to learn the appropriate words for such cases. The first word we're going to learn about is called an outlier. And so an outlier is a case that falls outside the overall pattern of the relationship. So there can be observations that are weird and strange, but not be outliers. So be careful. Here would be a case of a very strange point, but it's not an outlier because it's compatible with the pattern of the rest of the points. Here's a case right down here that is being circled with my mouse, and this is an unusual value and it doesn't follow the pattern of the rest of the points, and this one would be called an outlier. So I hope you're clear about that. Just because a point is weird doesn't make it an outlier. It's a crucial question of, is it compatible with the rest of the points? Here's another data example where we have college grade point average on an atypical non-standard grade point average scale and the IQ of the student on the horizontal axis. A point right here that I'm circling is a point that has a fairly typical IQ, a little bit over 100. There certainly are students with higher IQs than this, but it's not that strange of an IQ score. But the grade point average is terrible. This student is not doing well given their intellectual ability and their IQ. They might be known as a slacker or underachiever. In contrast, think about a point where a student like this one, they have the lowest intelligence of any student in the data set, but yet their grade point average is sort of reasonable. This is an unusual case or an outlier also. They have a pattern that's not really consistent with what the rest of the data would say. For the intelligence level of this case, we would have expected probably a grade point average down here about 1.5, but we didn't get that. We got about 7.5. So here's a case where there's a couple of outliers. The other values in this set of data is probably none of them outliers. Maybe this one, maybe 3 outliers in this case. Here's a reading score on the vertical axis and IQ on the horizontal. And I think a case like this one down here is an outlier. The child's IQ is quite high, quite strong, but the reading is really low reading ability. There's some sort of reading disability going on with a case like this one. So strange, probably an outlier. This case right down here is quite strange. This child has a very low IQ and also has a very low test score, but this one's probably not an outlier because it's basically compatible with the message given by the rest of the points. So I hope you'll ask questions about that if you don't understand that. There's another kind of point, and that would be a point that might be called an influential case. And this is one where if an observation is in the data set or not in the data set, the summary least squares line will change a lot. And so we worry about things like this where the story of our analysis is really being driven by individual cases. And so in our example we were looking at before, age 18, not age 18, but child 18 is an example of an influential case, because when child 18 is in the data set, the summary line is like this dark solid line. But if we get rid of child 18 out of the data set temporarily, the least squares line shifts dramatically to this dot dashed line right here. And so case 18 would be called influential. I don't think case 18 is really an outlier, especially. It follows the pattern that might be suggested by some of the other points. So I'm not sure case 18 is an outlier. It certainly is influential. Case 19 is an outlier, however. It has a value of IQ Giselle adaptive score that's notably higher than what we'd expect in atypical response compared to the rest of the data. The dashed line comes from removing case 2 and case 18. Without these two cases in the data set, there's almost no relationship between age at first word and intelligence. So this is an important thing to understand, that our negative relationship between age and intelligence is really driven by two data values, and you really should mention that in any analysis report that you have very influential handful of cases. Sometimes it's hard to judge whether summarizing a relationship with a straight line is a reasonable and good thing to do because of tilt in the scatterplot display. And so one way around that is to orthogonalize or make 90-degree angles in your displays and plot residuals on a vertical axis and, say, the predictor variable on the horizontal axis. And what you're hoping for, a good summary line will go through points such that residuals will be evenly balanced above and below 0 throughout the display. What we would worry about, this is a good looking residual plot, by the way, what we would worry about is something like this middle panel, when some of the residuals are negative at the beginning and then they're positive and then they're negative again. That would suggest that we're trying to put a straight line through a curved pattern. And the middle display would be a very disturbing residual plot that would suggest we're not doing something very wise. The top one is a very nice looking residual plot, even scatter or above and below a residual value of 0. I'm not going to talk about this bottom one. That's a different issue suggesting different variation depending on where you are in the display. So here is the residual values for the reading and age at first word intelligence example, and you can see pretty much an even scatter around 0 except for child 19, which is way above everyone else. This is a very unusual intelligence value. One of the things that you'll notice is that we've been talking about least squares lines, and sometimes these least squares lines are called a regression line, or this whole technique is called regression. Where did this word come from? Well, it came from an investigation by Galton, a relative of Charles Darwin, and Galton was a believer in eugenics, and you should read online about what it means, but it's a very disturbing kind of set of beliefs, and he thought that human value and human quality was transferred and could transfer from generation to generation. And one of the ways that he thought that human value could be measured was through height, and that height was a measure of human worth and human value, and that human value being transferable between generations would mean that fathers' heights would transfer to sons' height. And so this is the famous display that started this investigation. So Galton collected data on father and son pairs, and the points represent those data pairs. And you can see that taller fathers tended to have taller sons, shorter fathers had shorter sons, and this is roughly compatible with what Galton thought happens and should happen in humanity. Value and wealth and privilege should transfer from one worthy generation to the next, because value transfers genetically between offspring and parent. But the problem was, when Galton started looking at this scatter plot closely, there's a very disturbing thing happening here. Let's take a look at some really valuable fathers that are very tall, 72 inches in height, and their data values are in this strip of dashed vertical lines. Here's all the father-son pairs for tall fathers, 72 inches of height basically. And what you'll notice is the son's height for just the values in this strip is about right here. This is about the halfway son's height. About half the sons are taller than this number, half the sons are shorter, and what height is that? Well, it's about 71 inches. And that is really disturbing to Galton, because remember, these fathers are 72 inches of height. And their sons are tall, but not quite as tall as the fathers. Height is not transferring cleanly. The really high value fathers have valuable sons, but not quite as valuable as the fathers were. And if that's not bad enough, take a look at these really low value draggy fathers that are short. They're 64 inches of height. And let's take a look at their sons' heights in this strip. Their sons' heights halfway point is about here, and that's about 67 inches of height for the sons. So let's get this straight. The fathers are 64 inches of height, and the sons are even more valuable than the fathers at 67. And so Galton sees the pattern, and he's very disturbed and disgusted, and he sees a problem with the way he thinks the world should or does work. And what's happening is really high value fathers are creating sons that are less valuable, and the really low valuable fathers are creating sons more valuable than themselves. And he calls this phenomenon regression to mediocrity. Everybody's muddling towards the center in a big unimpressive mess. Perfect transfer of height would be represented by this dashed line between fathers and sons. And you can see that perfect transfer of height is not happening. The basic pattern of height is this solid line. It's much less steep and much more muddled. Father-son heights don't transfer cleanly like Galton thought or wished. Here is a way to get those lines on the father and son graph using R. I loaded the data. I made a plot of son on vertical, explained by father height on horizontal, and put some lines with a slope of 1, intercept of 0, and a slope from the best line for the solid line there. Sometimes summarizing data doesn't work so good in a scatter plot because of curved patterns or other kinds of problems with the measurement scale. And so sometimes we can summarize with straight lines anyway by just changing the scale of measurement. And this sometimes bothers students because it seems like we're cheating or just fudging and improperly changing the data. But something like the square root modification is really not terrible, because if a value of the response variable is big on the y scale, it's also going to be big on the square root of y scale. Think about temperature. A really high temperature day in Fahrenheit is like 100. That's still going to be a really high temperature day in Celsius. So it really doesn't change the ordering, it just changes the spacing in a plot. Here's kind of an example of one. Here's the original data: body weight of animals in kilograms on horizontal, brain weight in grams on vertical. And it's hard to see the pattern here because we have such a big range of big animals like elephant and lots of little small animals, and it's hard to understand if there's even a pattern here. But if we take logarithms of both the vertical and the horizontal axis variables, we see a new scatter of points that are quite linear and can easily be summarized. The same data values are still here. This is still the elephant up here with above average brain weight for the body weight. And, you know, these are still dolphin and human right here with very high brain weights relative to their body weight. And that's why dolphins and humans can study statistics. We've got bigger brains. And, you know, hippo is not a real bright creature relative to their body weight. And, you know, hippos are still here. There they are with below typical brain weights. And so the data has just been rearranged, but the pattern has not been structurally altered terribly. Let me know if you have questions.